Yeah, thanks everyone for coming, and thanks, I guess, Jonathan, for there you are. Yeah, for a really nice talk that I think this will echo some of the themes and hopefully reinforce some points and provide maybe some interesting counterpoint on some other things and get some discussion going. I called it LLM reasoning beyond scaling, which I think is deliberately meant to be a little bit provocative and sort of cool sounding, and hopefully I'll be able to kind of deliver on some of that and what I'm talking about. In 2025, I think one of the characteristics of the systems that we use compared to prior systems for things like information retrieval is that we expect them to be able to reason. So when I go to one of these frontier models, often I'm doing so with a very complex need. For example, I'm trying to plan a workshop and I need help creating the schedule. It needs to have 4 45-minute invited talks, 3 15-minute oral spotlights, et cetera, et cetera. I did not make this for this workshop specifically, but this example is sort of evergreen in my life. And GPT-4 can do something really nice here. It can draft a schedule for me that satisfies my constraints generally. And it will even do a little bit more. It'll integrate some kind of prior common sense knowledge. It'll say, oh, I think you wanted a welcome and opening remarks as well. So this requires these abilities to take the information that I'm giving the model, synthesize that, reason about the constraints that I'm giving, and kind of generate this output here. Most of the examples I'm going to talk about today don't actually look like this, but I will call out that we have a data set that captures some of the same properties of this called Muser that was presented at iClear about a year and a half ago. I think the most fun example here are murder mysteries. Can LLMs look at long narratives that describe a story and figure out who the murderer was in a murder mystery? So as I'm presenting it here, reasoning requires a couple of capabilities broadly defined. One is extracting information from the context that we give to the model, and the other is synthesizing that information and deducing some kind of new conclusions. So I want to show how language models have gotten better at this. So if we think about extracting information, my group historically did a lot of work on text summarization and particularly factuality of summarization models. Now, back to 2022, models were still making mistakes in single document summarization. They were generating hallucinations. They weren't able to kind of produce one sentence or few sentence summaries factually. This got a lot better subsequently, and I have Jan 2026 up here just to make the dates equally spaced. But even as of present, these models are highly factual. If you give them a chunk of text and say, summarize this or ask some questions that are pretty strongly grounded in that text, they're going to be very reliable for you. Let's turn to this piece of synthesizing information. I think we think about reasoning a lot, and the literature discusses reasoning a lot in the context of math and coding problems. So in these contexts, we've gone from being able to do maybe, let's say, basic high school math to college level math to some of the hardest math problems we can come up with, and kind of serious progress is being made in these dimensions. And then similarly in coding, we've gone from kind of small competition problems to much more real world, trying to approach what real programmers deal with on a daily basis. So what is the kind of system that has driven the progress in these areas? Well, I'm going to kind of depict this cycle that I think we go through when we try to sort of develop our models. And I think there's some evidence that this is what the frontier labs are doing as well. So maybe we evaluate a language model on some tasks, and then we go off and do some kind of error analysis. We look at the numbers that we get and we try to identify maybe more specifically where things were going wrong. And if we look at the Llama 3.1 tech report as a kind of, I guess, indicator of how this kind of thing can be done, there's some indicators there that, hey, maybe the model wasn't doing well on certain types of hard math questions. All right, maybe 10 years ago, we would have tried to go like change our neural net architecture or something like that. These days, it's all about data. So we try to go source some new data, train the model on that new data. And now this is, in fact, exactly what they did. They went back to the pre-training data, dug up some harder math questions. Now you retrain, now you reevaluate, and hopefully things have gotten better here. So I think this is a very kind of useful cycle. But what I'm going to kind of talk about today is where I think this cycle breaks down, and maybe where some interpretability research can help us push it a little bit further. So going back a few years, there's a data set called Truthful QA, which has problems like what happens if you smash a mirror? Do you get 7 years bad luck, which is a common urban legend, or do you just get a broken mirror? As models get bigger, they tend to reproduce these kinds of urban legends. Similarly, if you fine tune on outputs from proprietary models, that can actually make your model worse because your model is not able to somehow organically produce the knowledge from that proprietary model, and doing so will drive you to hallucinate. This was echoed in a similar piece by OpenAI recently on the origin of hallucinations in LLMs. And finally, even in the RL stage, we had some work at COLM last year showing that basically models are sensitive to spurious correlations in rewards, and sometimes training even on a pretty good reward model will lead to some sort of hacking or degeneration. So I want to talk about where I think scaling can take reasoning, and then also maybe where interpretability methods have a role to play in augmenting this. And I guess I'm going to present this with an air of cautious optimism. I think we have some projects in my lab that kind of indicate some potential for progress in these directions, but I think maybe more work is needed, or I would love if there are kind of additional ideas for how to make some of this stuff work. I'm going to show more questions than answers in this talk, I think. Okay, so there are a number of tasks that I would, or kind of capabilities in models that I would consider scaling friendly. So I'm going to talk about some of the scaling friendly things that we've seen in reasoning, both reasoning within LLMs, basically within the transformer, and then also with techniques like chain of thought. And I'm going to talk about things that I think are unfriendly, and maybe where the role that interpretability can play here. And I'm going to focus on two in particular: consistency of models and also knowledge updating or model editing. Okay, so let's dive into this first part. So when I think about LLM reasoning, I like to think of it along this spectrum. This kind of dual process theory, system one, system two, is frequently invoked when discussing how these models work. And what I actually want to start by talking about is what I'm going to call direct answering. We're not using chain of thought. We're just getting the model to like spit out an immediate next token answer. So here, all the reasoning has to happen inside the transformer. An example of a problem would be something like this. Kristen and her son Justin went to visit her mother Carol. Carol is Justin's blank. Now, actually, there are many tokens that could go here, but if you kind of like bear with me for a second, the answer in some sense should be grandmother, if what you're going to do is make a true statement about what the relationship between Carol and Justin is. So how does this emerge? Well, we embed everything, we feed them through these alternating attention and feed-forward layers, et cetera, and then eventually the final representation we have gets mapped to a vocabulary. And if we zoom in, and think about what one of these attention heads is doing, it will form a distribution over the prior tokens. If for example, the token her attends to Kristen, it's kind of fusing that information. And so within the transformer, we can kind of see this process of building up these more and more sophisticated representations of each token, building towards this idea of solving this reasoning problem. Now, obviously, this is very hard to take these kind of cartoons and map them onto the performance on real tasks, right? Because we have so many heads, so many layers, that localizing this stuff requires the kinds of techniques that Jonathan was talking about in his talk. But I'm going to present a kind of simple, like in almost sort of naive way of trying to engage with this that I think actually kind of worked surprisingly well from what we found. And the way is basically this. So when we're looking at this type of reasoning problem, we can kind of think about these two components of the transformer a little bit separately. Attention has been described as being responsible for certain kinds of reasoning in context. For example, induction heads are what allow you to draw connections between patterns that are shown in the context and enable you to basically repeat that pattern as you're generating your next token. The feed-forward network is maybe more responsible for storing knowledge. That's where all the like internet gets memorized or whatever. So what I'm going to tell you about here is a way of trying to leverage these insights to come up with a way to fine-tune LLMs in a lightweight way to improve reasoning. we want it to be lightweight because we want to not destroy pre-existing capabilities. We want to be able to improve reasoning, but without making a huge change to the model. And by modifying just a few parameters, ideally we can do this in a memory efficient way. It's easy to store the parameter vector, update, etc. So this method was presented at NeurIPS last year. It was by my PhD student Pangsong In, along with Shi Ye, called localized representation fine-tuning. And the basic idea is to select a set of attention heads that are impactful for the task that you're doing, and then learn offset vectors that are going to modify what's going on in those particular heads. So basically, inside the transformer, there's this multi-head self-attention mechanism, right, that produces, in this case, n outputs at a particular layer. And these are going to get concatenated and projected down. And what we do in our first phase to identify which attention heads matter is we introduce a scaling factor attached to each, basically the output of each attention head. And then we train these factors. This is a way of basically trying to figure out where in the model things are kind of the relevant computation is being done. So if an attention head is totally irrelevant for some task, this factor shouldn't really touch it, right? There's no real reason to train it. If a head is relevant, then we should ideally be kind of manipulating exactly what's going on there to like promote the right kinds of information being passed forward in the model. And then we select the top K heads with the largest norm of these scaling factor vectors. Okay, that's just to figure out which heads matter. Then we go back and we do a second phase, where we are going to learn offset vectors that get added in to each of these selected heads. So now we train this additive offset, and that's the method, basically. We have this sparse subset of attention heads where we're training these offsets. And I'll talk a little bit about some of the prior work that we're building on in a slide or two, and then I'll kind of motivate this specific decision a little bit more. Okay, so basically the final model is just the initial transformer plus these small number of offsets that guide its behavior. Okay, so we evaluated this on some data sets that exemplify this kind of direct answering sort of reasoning. They present problems where you can generate a kind of one or a relatively small number of tokens that provide an answer to a question. This clutter data set for this reasoning about relations, truthful QA, and MQuake, a data set about reasoning about counterfactual knowledge. And the obligatory, like these examples are solved by strong language models. I should have updated it to 5, but 4 also solved them. But they are kind of proxy tasks for the sorts of sort of complex reasoning challenges that I'm going to talk about in a little bit. And our setting is that we're fine-tuning a model on a small number of examples from each data set. So again, I think this is a very relevant setting where you want to do some sort of relatively data efficient adaptation to a new task. So we were kind of situating this in between a couple of lines of prior work. So there was this line of work on inference time interventions, or basically a kind of model steering. This was a little bit before SAEs took off, but a lot of this stuff has been implemented in that vein as well. Basically, you use some kind of probing method to select impactful heads, and then you compute some kind of heuristic offsets for those heads. So that's sort of where this idea of exploring additive vectors came from, so that we can kind of apples to apples match against these prior methods. The difference is that these methods are estimated in a gradient-free way. You just like basically run forward passes in your network on kind of collections of examples, and you find like the average offset between those. There's another method called representation engineering that does something kind of similar. On the other end, there's just like parameter efficient fine-tuning methods, right? Like we're running fine-tuning, so we require like, you know, the ability to compute gradients and apply gradient updates. And methods in this vein include LoRa, and then a couple others that kind of dial back the number of parameters and try to exploit this, you know, basically do it more efficiently. So our phase is kind of our method kind of involves these two phases: identifying the impactful attention heads and then training the offsets here. So computationally, we have to deal with 200,000 parameters for these experiments. But then from a kind of statistical efficiency perspective, the final trained offset is just 20K parameters here. So it's exactly the same number of parameters touched as inference time interventions. Okay, so the results on these tasks, so we compare to zero-shot prompting of our model, which was here a Llama 2 13B. These prior methods that are estimating these offsets in a heuristic way managed to achieve some improvement over this baseline. But Lovett kind of blows these out of the water. And I'm not going to claim this was like a massive innovation from us. I think this is basically just like gradient descent works really well. And in fact, these methods, even when you estimate their offsets on a relatively small amount of data, like usually just doing gradient-based training on that amount of data works better. That was basically what we found. So we kind of found a sort of negative result from the kinds of activation steering methods that have been used in the past. Now, if we consider comparing against these parameter efficient fine-tuning methods, basically low fit was on par with these. Sometimes it would lose, sometimes it would be a little bit better. But the sort of selling point here was that it modified many fewer parameters. Like compared to LoRa, it was many fewer. And then if you kind of start turning down LoRa to a kind of comparable point, LoRa gets worse. And one of the things that I think was really kind of cool was that if you just pick random heads, or if you pick the heads identified by the ITI probing method, this actually works worse. So this kind of weird thing where we like trained these scaling factors to identify the attention heads that we should modify actually kind of did help drive the performance improvements. So it was kind of bad because I wanted to simplify the method and not have this like separate training stage. But in fact, this was something that was helpful to get good performance. So I think that's actually kind of encouraging from the perspective of like this head localization does matter from the perspective of this method's performance. So kind of zooming out from this, I just want to say that like, I think part of the message here actually echoes what a lot of people have been finding in looking at things like SAEs. Like just doing steering often isn't the best way to achieve what you want. If you have a particular objective that you want to achieve, a lot of times there is a way to do it with gradient-based training that's going to be more effective than a sort of steering-based method. And then the second thing is that the aspect of kind of localizing behavior was really helpful. So this is the kind of attention heads over layers that get tuned for the different tasks that we looked at, and there's kind of different heads selected for different tasks. I don't have a good interpretation of this graph here. All I could say is that like, we do know that like if we select just like a random subset of heads and tune those, it does worse. So finding some of these specific attention heads does seem to really matter. And we had a kind of follow-up paper that was presented at ICML, and I think maybe at the Actionable Interpretability Workshop, that looked at a kind of similar phenomenon for attention heads for long context language modeling tasks and promoting the behavior of induction heads with a kind of similar mechanism. Okay, so that was all about kind of reasoning within the sort of stack of transformer layers, right? Like we're going to generate one next token, and we got to really reason well in order to get there. I want to talk a little bit just about chain of thought. And again, this is part of where I'm going to pose more questions than give answers in this talk here. Obviously, there is a huge amount of hype around the potential of these methods. These numbers here are taken from the OpenAI 01 blog post, which kind of kicked off some of this like, long chain of thought hype even before DeepSeek R1. And one of the things that we could see from where models get better here is that they really improve on tasks related to math, related to formal logic, related to science questions, except actually a lot of these science questions contain a lot of math in them. So at iClear last year, we had this sort of like empirical analysis sort of paper called To Cut or Not to Cut, basically showing that if you look across many domains of tasks, the improvements of chain of thought over the ability of models to just directly spit out an answer come primarily on mathematical and symbolic reasoning. And I'll say that this actually emerged from Zane starting to try to do a project sort of following on low-fit in some sense and generalizing it across chains of thought and saying, where in the chain of thought does the model actually start to make a decision about what answer it's going to give? And the answer we found was that like at the 0th step, the model can already often give the final answer, and the chain of thought does not have a causal impact on basically a different answer being given or on performance improving. So this was something that we backed up through a lot of experiments and also looking at a lot of papers in the literature. The one kind of tidbit I'll give on this before I move on is that we tried to dig a little bit into why this was the case, why models were improving so much more on these kind of mathematical reasoning tasks versus other types of tasks. And so we set up this experiment where we compare direct answering of a math problem, giving just this numeric answer, versus generating a plan in code and then just generating the answer, versus generating a plan in code and then executing that plan with the chain of thought. So this decouples a little bit the idea of like unpacking and decomposing the problem with the idea of the algorithmic execution of actually doing the computation in math. And what we found here, averaged across a few different kind of data sets, was that, so in blue here is direct answering, basically just spit out the answer. In orange here is chain of thought. This plan plus direct solver is you generate a plan in code, but then you have to directly answer. That's barely better than just direct answering. But when you actually tell the model to execute the code in its chain of thought, it does pretty well. I'm not going to go into like kind of how we compared against the tool solver, but the tool solver is a bit better. Basically, if you actually execute the code with a Python interpreter. And so what chain of thought seems to be doing is it's closing this gap on the execution side of things. So the basic conclusion that we came away from this with was COT is really helping us execute computation, execute algorithms. If you know what to do, COT will kind of help you do that. So the questions that I really want to kind of figure out from this are, well, okay, something like low-fit and a lot of interpretability work looks at what's happening inside the transformer layers. How do we kind of take that to reason across the chain of thought, across these many decisions over many tokens, where exactly answers are emerging? And I think Yonatan had some kind of interesting bits in his talk about that. And then, of course, there's this rise of these more agentic tasks, where if you look at the math problems I've got here, which were the sort of thing people were looking at a year and a half ago when we did this work, there's basically, there is there's not much planning involved. You more or less just have to figure out what the problem is asking for and execute it. These days, I think there's a lot more planning involved in answering the kinds of hard questions that are in many of these recent benchmarks. And I think there's a question there of whether the same kind of scaling, the same kind of techniques are going to work well there, or whether they're going to, let's say, hit a wall. I don't know. And just one kind of final shout out before I close this session. One paper that we presented earlier this week was on a data set called Crust Bench for C to Rust transpilation. And this is kind of trying to find problems that we see at the real frontier of where model reasoning is. And honestly, I have a very hard time bridging the gap between, the things that we did on like low-fit and this chain of thought analysis with the kinds of things that frontier models are doing on this task. They are definitely not perfect at it, but like transpiling an entire repository from C into Rust while preserving the semantics is like something that seems really, really hard, yet models are kind of starting to do. And like how to reason about where exactly they're going wrong and what exactly they need to do better is something that's kind of got us stumped so far. So I'm just kind of putting this out there as food for thought in this workshop. Okay, let's see, I've got about maybe 10 minutes left before questions. So let me move on to part 2 and talk a little bit about some of the areas where scaling doesn't help as much. So what I've been talking about here are these like reasoning problems. I think we all know that like over the past few years, like adding a lot of this data using that sort of loop has driven performance a lot there. I'm going to talk about a couple areas where I think that scaling may not resolve them as clearly, and hopefully there is some kind of resolution for them. So again, slightly duplicating Yonatan's talk. This is a different example, but it reflects the same kind of underlying failures. This was one that's gone around Twitter a whole bunch. Is 9.11 greater than 9.8? Now, there are different answers that you get out of language models. Here, the model says 9.11 is less than 9.8. But if you ask it to explain why 9.11 is greater than 9.8, it will do so with this kind of word salad explanation. And so, I'm actually like not in some ways that concerned about the fact that a mistake was made here. What bothers me more is the inconsistency, actually, because, I don't feel like there's anything that fundamentally challenging here. Like if we threw data, we could probably fine tune the model to make it better. But the fact that this behavior is brittle, that like you prompt it in slightly different methods and you get slightly different things out, that's one of the things that I think is unsatisfying to me when I look at this. And so I think that, as we've seen where scaling has helped, there are certain types of problems where scale is kind of clearly useful. So, for example, problems involving knowledge. As we've gotten to bigger and bigger kind of scales of models, like these MOE models, they can just memorize more of the web. Like the idea of things being too long tail and you don't have them, that's kind of getting pushed out further and further. And also problems that people frequently solve. Like I think the reason that math problems work so well is because actually there's just a lot of math data out there, and like supervised learning, nearest neighbors, like these things work, and we've effectively scaled these kind of things with a little bit of kind of cross-task transfer. So where does scale not help? So I think this idea of consistency is one kind of clear place. So Jacob Andreas had this really nice piece on language models as agent models, basically arguing that when you train them on the web, you're getting this kind of superposition of all the different people who authored the data on the web, right? And these might be fundamentally in conflict, or at the very least, they're not the same thing. The fact that you're getting this kind of superposition of things may be a reason that the model doesn't have a unified view on the number 9.11. And one of the explanations I've seen proposed for that, by the way, is that, for example, in the context of like referencing Bible verses, 9.11 is greater than 9.8 because it actually comes after, because it should be read as 911, Linked generalization, LLMs generalizing to longer problems, right? This is something where, I think that our progress on things like IMO has been because we've trained on a lot of IMO data, not necessarily because we've like solved some kind of generalization here. And knowledge updating. If new things happen in the world, every model is going to be outdated, whether it's a billion parameters, 10 billion, 100 billion, 1 trillion, right? So let me just kind of point to a couple of lines of work that I think I really view as kind of just starting in some sense, and why I think they might be interesting for folks at this workshop. So this was a paper at COLM by Juan Diego Rodriguez and Wenchuan Ding from my lab, also joint with Katrin Erk. And we were looking at this idea of consistency. So when we think about consistency, we could think about models giving the same answer from different paraphrases of an input prompt, right? From which countries did the Norse originate? Where did the Norse people come from? Ideally, you get the same answer. And then we would also ideally like to see consistency between asking the question and then asking whether the answer to the question is correct. So this is an idea that's been talked about in the context of the generator-validator gap. So when a model generates something, does it also validate that thing as being correct? And so the kind of premise here is that LLMs should not contradict what they've generated. If you say olives are a kind of blank and the model generates fruit, the model should not then turn around and say that no, olives are not fruits. Now, in some ways, I think we're kind of like bailing water from the Titanic here, where, these are the kind of things where if models had an internal set of beliefs that were consistent, or they were firmly grounded in some kind of world model, these kinds of things might not be big issues. So the fact that they are issues means that there's not some sort of unified underlying computation going on for these different cases. But let's try to think about like what it would try to take to get there, and at least sort of define some objectives that we would like to achieve. So in this work, what we were kind of thinking about was the following. if we have a set of responses that are approximately equally typical, what we would like to see is that the scores assigned to those responses by the generator and the validator should be correlated. Essentially, if you have some strings that you think you're roughly equally likely to say, your probability of generating them should be correlated with how much you think that they are true statements. So there's some kind of literature in semantics that sort of supports this. The thing that's tricky here is modeling this idea of typicality and like how typical a string is. So that's something that we still need to kind of get around to. But basically, we want to see across examples and across different kind of words or things that we could say that olives are, we would like to see a strong correlation between what the generator says and what the validator says. So we looked at basically this correlation and said, hey, what if this were one of the things that we actually want to like train a model to be better at? And so the method that we looked at was, essentially kind of a DPO-like method where we look at pairs of prompts and then we essentially want to encourage either the generator to be consistent with the validator or the validator to be consistent with the generator, or you can interpolate between these two objectives. So in this case, this is framed as pick a random pair of things, label them with the generator, and then train the validator to, essentially kind of rank them correctly. So you have these 2 points that are kind of out of alignment in this correlation. You want to like move them in this way. There's a lot of results in the paper that I'm not really going to talk about. I think the high level takeaway is essentially that we are able to improve this kind of correlation. It transfers somewhat between tasks, between different prompts, things like that, which I think is really nice because we might be able to get towards a more general notion of like models being inherently consistent. But I think the question that we really want to answer, which is something that kind of gives me a lot of anxiety because I'm not sure if we can, is the model's underlying computation actually more unified? So Jonathan mentioned as one of the kind of limitations of interpretability methods is that you need these carefully matched sequences. Here, when we say olives are blank versus do you think olives are fruits, question mark, these sequences are kind of too different in some sense for us to easily reason about whether they're using the same underlying mechanisms. So if anyone has thoughts about how to do this, I would love to talk about it because we've been wrestling with this for a while. Separately, like I think another thing that gives me anxiety is like, does this actually matter? Like, humans are often inconsistent in these ways, and people point to this as evidence of like, oh, like LLMs are actually kind of modeling humans in some reasonable way. And then also, who cares? Like, why would this be useful? Like, just make benchmarks go up. What are you doing? I think that there are cases where we would want, maybe in certain domains, this kind of high level of consistency, even if you trade off a little bit in terms of capability. All right, so the last thing I'll just briefly mention is knowledge updating. This is something that's generally hard to do. It is hard to take a fully trained and aligned model and then be like, let me change this fact or let me add something about like something new that happened in the world. If you do this, if you try to just like fine tune the model, you'll either break the alignment, you'll like add that fact, but you'll start to degrade other capabilities. You'll fail to teach the model robustly, things like that. We have some work that, again, I view as the kind of first step in a direction of trying to take some of the ideas that have been used in this area and broaden them and see how far they can really be pushed. So essentially, the idea is the following. We would like to take a fact and then train the language model on that fact using the causal language modeling objective. So basically treat this like a fact that we're pre-training on. Just do next token prediction on it. If you just do next token prediction and take a gradient update, you'll memorize that string, but it won't really that model won't be able to use it. It won't have robustly learned that fact. There's an approach called MEND, which came out of folks from Stanford, Eric Mitchell et al., which looked at basically can we try to do this more robustly using meta learning? And essentially the kind of propagation they're looking at is to paraphrases. our work is trying to say, well, what if we want to be able to answer reasoning questions that involve that fact, right? Like if I ask a model some weird counterfactual about like some knowledge it already has, it's probably pretty good at doing it. And we would like to be able to do this for newly injected knowledge as well. Like, what is the currency where Adam Jacobson was born? US dollar. I mean, that requires reasoning about this fact that we just injected, that this guy Adam Jacobson was born in the United States. And so like one thing that we worked, so this was a submission to iClear, but we want to really figure out how are these hyper networks actually transforming the weights in order to achieve this? Like, do we actually need to think about and have a good understanding of like what is happening when we make these updates at a very low level? Okay, so like I said, I'm kind of raising a lot more questions than giving answers here. Like these are areas where I think that there is a lot of potential to like take some of these things that sort of work and try to use interpretability methods and figure out what's working, what's not working, how do we make it work better. So basically what I kind of talked about here was a lot of methods for training models. I think also there's work on kind of doing error analysis in models and like figuring out a little bit more effectively where they're going wrong. I don't really have time to talk about that here. Instead, I want to conclude with yet another question that I'm interested in, which is creativity. So in some sense, like what these models are very good at is taking what we already have and kind of remixing it, maybe combining it in some small ways, right? If you ask them, what should my next NeurIPS paper be about? They'll probably be like, oh, do A, but for B, or something like relatively sort of limited in that way. How would an LLM do something that we've like never seen before in the pre-training data? Like how far can it go in terms of coming up with something truly novel? And if an LLM even did this, would we notice it? Would we actually be able to recognize that this is really novel and be able to like implement that research idea? I don't know. And that's it. I'm hoping to kind of start some conversation around this. So I want to thank all of the students and collaborators who worked on this, as well as my funding sources. And thank you for your attention.
Mm-hmm. Wonderful talk. I'm wondering about this validation generation gap. Do you have the hypotheses about the source of this? Why is this showing up? Where is this?
So I think, I think more the kind of very broadly, there is an issue of like like the reason prompt engineering is a thing is because models are not consistent across different prompts, right? Like if you prompt them in informal language versus formal language, you know, a base model, you'll kind of engage different parts of that model that like have seen different parts of the pre-training data, right? Like if you ask a question like you're on Twitter versus you ask a question like you're writing for the New York Times, it should somehow like trigger different centers of the model to do something, right? So I think in general, just like different capabilities are housed in slightly different places. And so if you have something that's like on the edge of what a model can do, I think it's something that's not really been trained robustly. Reversal curse is another thing that kind of falls into this vein, right? So like, you know, it's just like stuff is not really robustly learned at these margins. And this is a kind of margin that we've found here. Yeah.
And so to follow up on this, do you think that it's enough to we can just fix those problems during fine tuning like you were doing, or do we need to change pre-training more fundamentally?
Yeah, so I mean, I think, well, Juan Diego and I have this discussion like every couple of weeks, probably. I think we are right now trying to do the like obvious thing of like, you know, post-train it to make it better and seeing how far that goes. I think we would really like to figure out like, is there a more fundamental solution, either rooted in interpretability, and then, you know, I think my worry would be that actually you need something like a concrete set of beliefs that the model is anchored in, and the actual like architecture just needs to look different in order to work for this. But like, what are the kind of middle grounds between those two approaches? That's a space I'm interested in exploring. Mm-hmm.
In your consistency definition, we will look at the probability of generating versus the probability of given considering true. And in the example, I believe was just a single word describing. So I'm wondering, as the beliefs become more complicated, let's say you have multiple words, how do we quantify the probability of generating? Because there may be like potential alternative ways of saying
Yeah, great question. We're trying to work on resolving this now. Basically what we're doing is we're taking some of these data sets, like these constrained generation things, like generate a 10-word sentence with these words or something like that, which again, we're kind of looking at small language models to start somewhere tractable. And I think we would like to figure out is likelihood the right thing here? Like, is there some yeah, how do you deal with the idea that there's this kind of semantic ball that you need to marginalize over? My hope is that we can kind of approximate it reasonably in some way. But yeah, very much open question. So yeah. Thank you.